All right, kiddies. So in this last section that we're going to cover in chapter 4, 4.8, we're going to discuss Newton's method for solving equations. It's a tangent line method using recursive tangent lines. And so I'm going to take a look at one simple example to show this. It works the same for no matter what the function is that you're trying to solve. The only one thing that's important about this example or any example is that you need a starting place. And so for this function, where we're trying to find where x cubed is equal to 12. Okay, now you might say, well, it's the cube root of 12. We're trying to approximate a value of x. That's going to make that true because it's an irrational value. Bring the 12 over, and that gives us our function f of x is equal to x cubed minus 12. So the recursive formula for these approximations is that x sub n plus 1 is equal to x sub n minus f of x sub n divided by f prime of x sub n. So we need the derivative of this function. So it's the first thing, might as well do that right now. It's real simple because our function is f of x equals x cubed minus 12. That means that f prime of x is equal to 3x squared. And we're going to use the starting place because, again, you must be given a starting place. You don't just make up your own, although you could, but for the most part in the book, they're going to give you x sub 1. So let's say that x sub 1 is equal to 2. So that's our starting place. So if you're given x sub 1, then your first approximation is going to be x sub 1 plus 1 or x sub 2. That'll be your first approximation, by the way. Okay. Now, what I've done here, since is going to be a lot of, once you get past the first few approximations, going to be a lot of decimals. You're going to rely on your calculator because your calculator will store these values for you. And in the book, some of them are going to be asking for maybe 4, 5, 6 decimal places of accuracy. So you can't do a lot of rounding. Make sure you know how to use your memories and your calculator. So what I've done here, and I'll show you this in a second, is I've taken the function f of x equals x cubed minus 12, and I've taken the derivative f prime of x equals 3x squared, and I've graphed them in the calculator so that I can easily so I can easily extract those values when I need them. Now I'm only going to do a couple approximations here. I'm going to go up to x sub 3. So on quizzes, labs and exams, I'm probably only going to ask you to go to x sub 3 because I basically just want to make sure that you know how to perform this recursive approach for solving these kinds of equations. Now, in the book, they might ask you to go to x sub 6, or in WebAssign, they might do the same thing. So notice what I'm going to do here. I'm going to enter my function x cubed minus 12 and my derivative 3x squared. It'll just make it easy to extract the values that I need here. Let me set my window. Let me go from -1 to 4. And I go from -6 to 12. All right, let me tighten up my window a little bit here, please. I'll show you these graphs in a second, okay, guys? And again, I'm just playing with my window, so just give me a second here. All right, so this should work fine. There is the graphs of the functions, the original function and the derivative. Now I'm putting this on the same screen so that I can easily extract these values here. So I'm going to take my starting value of 2 and plug it into each of the original equations. I don't really need my calculator to do that. I can do that by hand. Okay, so I have x sub 1, x sub 2 is equal to x sub 1, which is 2, minus f of x sub 2. So I'm going to go second, calculate value 2 on my calculator. That gives me -4. And then to the derivative, it's over 12. So this means it's equal to 2 plus 1/3. So that's, let me see, that's 7/3. So that's my first approximation. Now I'm also gonna, just for those of you who, that's approximately equal to 2.33 repeating. All right. Now let me show you what I've done here. I've plugged in my starting x sub 1 into that recursive formula, and I plugged in 2 into the function and the derivative. And basically, I'm using my calculator. Even though I really didn't need it for these, I did anyway. Okay. So there's my approximation. Now I'm giving the approximation as a decimal, 2.33 repeating. That's what 7/3 is. Okay. So let's do it one more time. Let's find x sub 3. So finding x sub 3 means that now I'm going to use this x sub 2 in the formula. So therefore, x sub 3 is equal to x sub 2, which is 2.33 repeating, minus, I'm going to plug in 2.33. I'm going to go second calc value, 2.3333 repeating. And that gives me 0.703. Okay, 0.70316 divided by, and we'll scroll up to the function, 16.3329. All right, let me show you this before I plug this in and get my decimal equivalent. So this is what I'm doing, okay, to extract those decimals from the calculator. And notice that I've written them in here. And now I'm actually going to come up with the calculation by just using my calculator. Yeah, you're going to rely on your calculator. So let me clear this screen. And let me plug in 2.333 repeating minus 0.70316. 0.0316 divided by 16.3329. And that gives me this. All right. So this is the value for x sub 3. This is my after my starting value of x sub 1 was given to me as being equal to 2. This is my second approximation called x sub 3. So this is approximately equal to 2.2902 8. Okay. Now I'm using 5 decimal places of accuracy here. Now, the only reason I'm only showing you like 2 of these is because this is a recursive process. You just keep on doing this. Now, once you have x sub 3, you would actually store that. The best way, now that we're accumulating a lot of decimals there, the best way to do this would be to store that value and then reuse that again to calculate x sub 4 and so on and so forth. Yeah, it's redundant, and it becomes a laborious task, especially in the book when they're asking you to find x sub 6 or x sub 7. It's kind of ridiculous. I won't ask that, but they do in the book. Now, what I want to show you is this value, 2.29028 approximately, okay? Okay. That's my second approximation, given the starting value x of 1 equals 2. That's my second approximation for the cube root of 13. All right, 2.29028. Now, what I want to show you on my calculator is, what does my calculator say the cube root of 13 is? So let's see. It says approximately 2. Oh, sorry, cube root of 12. My mistake. Try this again. Cube root of 12, not 13. 2.2894, and so on and so forth. So all we've done basically was just 2 approximations, and we're already pretty close to a good approximation for it by using Newton's method. By the way, if you ever wondered how a calculator can come up with an answer for the cube root of 12, it's because it uses this recursive method, except it does it 20 times. And it gets to within 20 decimal places of the actual value. Okay, so this is Newton's method, folks. Now, the last section in chapter 4, which is 4.9, that is going to be covered with the chapter 5 material. That's why this is the last Zoom recording in this chapter. Okay, everybody keep track of when everything is due. Don't be late. All right, guys, let me end the recording.